So we are starting the last part of this chapter, which is about solids, and we're going to talk about a little bit of, some martyr materials and how some of this chapter can relate to biochem. Okay, so these are all the different types of solids we're about to cover. You can read all about them, but we're going to go into detail about each one. So metallic solids are metals bonded with other metals like themselves, like a bunch of zinc atoms in a metal, a bunch of silver atoms in a piece of silver jewelry, a bunch of platinum atoms in platinum jewelry, okay? And the cool thing about metals is that they're electrons, right? Most metals tend to want to lose electrons to become cations. So in metallic bonding, the metals lose their electrons, but they don't lose them to like a non-metal. What happens is those electrons kind of flow through the metal in a sea of electrons where the electrons are just kind of flowing in between all of the metal atoms. They're called delocalized. This is what gives us all of our special properties of metals. They're malleable, meaning you can like bend them and hammer them. They're ductile. They can be stretched into thin wires like copper wiring. They have really high melting and boiling points. It's really hard to get a metal to turn into a liquid and or to boil, okay? Now, because of this sea of electrons, they're really, really good at conducting electricity. So it doesn't work on here, so I'm going to show it to you on here. So what I mean by this sea of electrons that is responsible for like the ability of heat and electricity to flow through it is, let's just pretend this is like a zinc atom, right? Zinc tends to lose 2 electrons, so zinc, 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 okay? Well, the electrons that all the zinc atoms lose flow between all of the other zinc atoms. So that's what allows heat and electricity to flow. It's this metallic bonding and the property of it that lets that happen. So again, this is like the sea of electrons where the electrons, they don't come off of the atom, but they do flow freely between all of the metal atoms. Okay, so this is metallic bonding. Okay, alloys are generally made of metals that have more than one element, and most of the time, we're going to do one exception, those elements are other metals. So these are like a bunch of different alloys that we're pretty familiar with. So look at brass is an alloy. It's consistent of copper and zinc. And right, these guys mostly are homogeneous, meaning when you look at them, the coloring, it looks even throughout, right? A piece of brass it all looks the same color, but it is a mixture of metals known as an alloy, right? Bronze is copper and tin instead of copper and zinc. But again, these are called alloys. So the main types of alloys that we're concerned with are substitutional and interstitial alloys. A heterogeneous alloy is just an alloy where the materials aren't evenly mixed, just like a heterogeneous mixture. I'm more concerned with substitutional and interstitial. So, for example, 14 karat gold is made up of gold atoms, right? So you got your gold atoms right here. And then some of the gold atoms are substituted, meaning like taken out and replaced with silver. So 14 karat gold is mostly gold, but has some silver substituted in for some of the gold atoms. So in substitutional alloys, usually the things that are being substituted are similar in size, okay? Now, interstitial alloys like steel are a substance, and for the most part, it's iron for steel. Iron is the main component. And now nothing is taken out and replaced. What happens is this carbon comes in and like kind of sticks in between the gaps between the iron atoms. Because of this allows the steel to be so rigid because the carbon is coming in and filling in the gaps in between the iron atoms and making it super rigid, so like the iron atoms can't readily slide past each other. Okay, so that's called an interstitial alloy. So look, we have some pure metal, and then for substitutional, one of the metals is removed and replaced with another metal. For interstitial, nothing is removed and just small atoms are stuck in the gaps between the metal atoms. And then this is like a mixture of both, which we don't talk much about interstitial and substitutional combined. Okay. So here we go. We have brass. Now I've noticed like this copper is like pointing to the wrong atom, right? Copper is going to be this copper-looking atom. So brass, substitutional alloy, a bunch of copper, and then some of the coppers are taken out and replaced with zinc, substitutional. Steel, a bunch of iron atoms, and carbon comes in and just fills in the gaps, interstitial. Okay, so we have, for solids, we have metallic solids. Those are just metals. Copper, silver, gold, aluminum, whatever, just metals with themselves. We have alloys, which are a mixture of metals. Those are kind of solid. And now we have ionic solids. These are our salts. So ionic solids have a unit cell that's like the basic component of it that repeats itself over and over and over and over again. And you have ions at the lattice. Now, there's different types of ionic solids and different types of how the lattices form, okay? But they're always done like charged particles. So for the basic example, the most common ionic solid we talk about is salt, sodium chloride, right? So it's Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus, Na, oops, whoop, whoop. This is Cl minus, Na plus. So this would be like a unit cell right here, the basic like component, for example, and then it just repeats itself over and over and over and over again in a very, very organized structure. So this is your crystal lattice. Okay, and all ionic solids do this. Now, they're not always in this kind of cube. There's different kinds of structures, but this is just the basic concepts that we need to understand. Now, because they are very, very well organized, ionic solids have really, really high melting points. They're really hard to melt, okay? In terms of like a hierarchy, for right now, for a brief moment right now, ionic solids are the strongest held together types of substances, ionic bonds, and then below ionic bonds are covalent bonds, and below covalent bonds are intermolecular forces. Okay, so we're at the top of the list right now for strength for a brief moment. There is going to be one type of solid that is going to be above ionic solids, believe it or not. Most ionic solids are soluble in polar solvents. That's because of our ion-dipole interactions. And right, ionic solids, we often refer to them as salts. Okay, and remember, we're talking about metal and non-metal, or metal and polyatomic ions, okay? And when they dissolve in polar solvents, they break apart into charged particles, and because of that, they are electrolytes, meaning electricity can flow through them. Also, when they're molten, aka turned to a liquid, they can conduct electricity, but they cannot conduct electricity in their solid state, because in their solid state, the charges are balanced out. Right? The positives are with the negatives in the solid state. So there's no electricity that is able to flow through it. Remember, the more charged particles or the more ions in solution, the better it conducts electricity. And again, the crystal lattice, pretty much the structure of ionic solids, is held together by positive and negative electrostatic forces. They don't share electrons. One thing loses the electron or electrons, the other thing takes it, and they become positively and negatively charged particles that are attracted to one another like a magnet, and that's what holds ionic solids together. Oh, I'm not screen sharing. You guys know that you had the whole time that you could have like unmuted yourself and asked me, right? Oh, I don't hear you at all. Are you guys talking?
Yeah, we're
talking.
Oh my gosh, I just can hear you. I'm so sorry. Wow, I can hear you now. What the heck? I was just sitting here talking to myself. I'm so sorry. Okay, so I went a little fast then, if you guys were asking questions. I know you weren't screen sharing. You could have followed on the Pear Deck, though, even though I wasn't screen sharing. I'm screen sharing now. Do you guys have any questions about any of the stuff that I just did? metallic bonding alloys, and now we're on to ionic solids, which are our salts. Okay, I'm so sorry. Okay, so again, what holds ionic solids together? Well, remember this is Coulomb's law, and remember this just means force of attraction, and this is just some constant K. We don't have to pay attention to this. And the force of attraction in an ionic compound, for example, depends on the charged particles. That's what Q stands for, the charges, and the D is the distance, so how far or close they are away from one another. So like sodium chloride. In order to get sodium chloride to break apart, you have to put in energy. It's very endothermic. So that is based on the fact of the charges that hold them together, the pluses and the minuses. This is the electrostatic force, as well as how close or far away they are from one another. Now, I don't know if you've ever done this, but you can try this at home, assuming you have water and you have salt. You can take a cup, make sure it's just room temperature. I would do like a glass cup and dump, if you're willing to lose, dump a bunch of salt in it at once, like a ton. It will feel cold because that process is endothermic. The dissolution of salt is endothermic. Now, if you don't put enough in there, it's hard for you to actually like feel it with your hands. If you had a thermometer, you could put it in there and see that the temperature will drop a little bit because the dissolution of salt is endothermic. Salt held together fairly tightly. It's an ionic compound that has charged particles. So it's not that it won't dissolve, it just dissolves endothermically. So just like analogous to bond energy. So let's flash back to bond energy. Bond energy is for covalently bonded molecules. Remember the difference between molecular are our nonmetals with other nonmetals, is different than ionic. Ionic are metals with nonmetals. So molecular compounds are held together with covalent bonds. So what holds them together is bond energy. So like a single bond is the weakest bond and a triple bond is the strongest bond. So remember, higher bond energy means harder to break apart. So analogous to bond energy is lattice energy, but lattice energy is for ionic compounds because they're held together in a crystal lattice. So the larger the lattice energy, the harder it is to rip ionic compounds apart. So the stronger the Coulombic force. So the first factor that plays a role in lattice energy is the size. The closer two ions can get to one another, the stronger of a Coulombic force they will feel. Think of them like magnets. If you have two magnets and you put them close to each other, they're going to want to stick together, right? Because they feel that force of attraction. Whereas if they're far away from each other, they won't be able to interact as strongly. So the size of the atom, or the ion, I guess I should say, will determine who has a bigger or smaller lattice energy. So in this question, I gave you the two ionic compounds. Which one has the largest lattice energy? Which means which one would be the hardest to break apart? Which one is held together more tightly, and why? Anyone want to share what they think it is? So they both have chloride in it, right? So it's not going to be the chloride. So it is the lithium chloride, right? Lithium is smaller than chlorine. Than potassium. Lithium is up here, potassium is down here, which means the lithium and the chlorine can get closer to each other because of lithium's smaller size. If they can get closer to each other, they will experience a greater Coulombic force of attraction and therefore have higher lattice energy or harder to break apart. Okay, now the next one that matters for lattice energy is the charge, right? So lattice energy is for ionic compounds, and so we're talking about charged particles. So the charge plays a role. So Q1 and Q2 are your charges in that Coulomb's equation. So charge trumps size, meaning if you have to choose between the two, charge plays a bigger role in lattice energy than size does. The more charged the ions are, the stronger or greater the lattice energy. So if I have magnesium oxide and lithium chloride down here as my examples, which of them has the largest lattice energy? Magnesium oxide or lithium chloride?
Lithium chloride.
Well, I just said that charge plays the bigger role than size, right? So magnesium is +2 and oxygen is -2. That is more charge than +1 and -1. So even though magnesium is bigger than lithium, the charge, it plays a greater role. So magnesium oxide is harder to break apart. It has greater lattice energy than lithium chloride. Okay, so having said that, I'm going to give you a minute for these ionic compounds. So the question says, right, so the whole point of these forces that we talk about, so right now we're talking about lattice energy, is that it determines these physical properties. It determines when things melt, it determines when they freeze, it determines when they boil, and so forth. It helps determine what states of matter they are under room conditions or whatever conditions. So which of them would have a higher melting point? So let's talk about what a higher melting point means. A higher melting point means harder to turn from a solid to a liquid. So to get it to go from a solid to a liquid is more difficult. So if it's more difficult, it would have a higher lattice energy. So I'm going to give you a minute to pick between each of these pairs who has a higher lattice energy. So I'm going to give a minute, please. These are my answers. Does anyone have questions before we move on? Okay, let's keep going then. So given this one, it says, which of the following metal fluorides, so it's some metal with fluorine, okay, or F minus, right? Fluoride is F minus, would have the lowest melting point. That means the easiest to melt. So having said that, which color sphere is fluoride? You should be able to know which color sphere is fluoride based on these. They tell you that they're both metal fluorides. So which color sphere is the fluoride? It's red, right? They both have fluoride in them, so they both should have at least one of the same ions. Then this means these are the different metals, this dark blue and this purplish blue, okay? So which one has the lowest melting point? Therefore, the lowest lattice energy, your smallest lattice energy, and easier to melt. So who's it going to be, A or B? It should be A, right? Because this guy experiences a weaker Coulombic force because these atoms can't pack in as tightly because whoever this metal is much larger than whoever this metal is. So therefore, it'll be easier to weaken the charges, the electrostatic force, to get it from a solid to a liquid or melting. Okay. Please, please, please pay close attention to this problem. I've seen it fairly often on the AP test. I put it on my tests, and for some reason it's always missed. But it says it's based on Coulomb's law, which is just the law of force of attraction being dependent on charge and distance. Which of the following would have the weakest interaction with an adjacent water molecule in an aqueous solution? And then they give you 4 different metals, and they have their radii. So the weakest interaction between a water molecule, which is polar, anybody know? It is barium. Why? Barium is the largest, and therefore it can't approach water as closely as the other 3 ions, or cations, I should say. So it would have the weakest interaction. Who would have the strongest? I know it didn't ask that, but who would have the strongest? Aluminum, right? Because aluminum is the smallest, meaning it can get closer to water and experience a greater force of attraction. Notice these are all metals. Metals tend to be cations, okay? Okay, now molecular solids. Now we've spent a lot of time on molecules, okay? Molecules are covalently bonded, that we drew Lewis structures with them. Remember, molecular for us in generally means non-metals only. Okay, and the thing about non-metals is that non-metals have all sorts of different states of matter. They have the most variety. Like our metals, almost all of our metals are solid, except for mercury. It's like the only metal that's not solid. Our non-metals have a wide variety of states of matter, right? Bromine's a liquid. Some of our metallic our non-metallic compounds are liquids under room conditions. Some of them are gases. So they have like a wide variety of states of matter. Now we've talked about liquids and gases, but we're going to focus this part on solids. So remember, molecular compounds are held together by covalent bonds, but the molecular solids, in order for them to be solid, what holds them together are our forces: dipole-dipole, dispersion forces, hydrogen bonding. Okay, and these forces are for molecular compounds only. So like ionic compounds don't have dipole-dipole. Now they do have the potential of having ion dipole, but ionic compounds don't hydrogen bond, okay? And so again, these forces are what determine a lot of our physical properties. It also determines like what states of matter they are under different conditions, all right? So again, for a molecule to be a solid, it's because the forces that hold it together are strong enough to turn it solidified. Now, molecular solids, because they're only held together by intermolecular forces, generally are really soft, unlike a lot of our metals, right? They have fairly low melting points. They melt fairly easily. That's because of weak attractions. And they don't conduct electricity when they're dissolved in water. So sucrose, for example, is table sugar. It's a molecule. Why? Carbon, hydrogen, and oxygen. Sucrose's formula is C12H22O11. This is a molecule, non-metal, non-metal, non-metal. It's an organic molecule, but it's a molecule, okay? And it has small molecules at the lattice. So what does that mean? Well, I'm going to use, just to do my best, I'm going to use this organized lattice, which is not exactly how molecules line up, but I'm going to just show you what it means. And I'm going to use water, for example, is that, right, in ionic compounds, this is a positive and a negative and a positive and negative. For molecular compounds, these are like the whole molecule at each point. So when it dissolves, it just dissolves into smaller parts of each molecule, okay? It doesn't dissolve into charged particles. And because it doesn't dissolve into charged particles, it can't conduct electricity. So our molecular solids don't conduct electricity. Molecular solids are the compound itself is held together with covalent bonds, which are strong, but what holds all the molecules of these solids together are intermolecular forces, which are relatively weak. So there's kind of like this hierarchy, right? It goes ionic bonding, covalent bonding, and then covalently bonding particles can be broken down into different intermolecular forces. So I'm giving you, these are 4 different examples of molecules, non-metals that can be molecular solids. So phosphorus is a solid, sulfur is a solid, iodine's a solid. Solid carbon dioxide is known as dry ice, right? All 4 of these solids are nonpolar. They don't have any dipoles. So the only thing that holds them together are dispersion forces. So you might think, though, that dispersion forces are weak, right? In general, they're weak. And so why would these things be able to stay as solid and not want to escape into the gas phase? Well, remember, the heavier that things get, the more or stronger the dispersion forces, the more polarizable they are. And the more polarizable they are, the better of a chance they can be attracted to themselves and stay as solids. Now, carbon dioxide can be forced to be a solid, right? Dry ice. But guess what happens when you take it out of its container? It readily escapes into the gas phase, right? It sublimes. It's called sublimation. Because of these 1, 2, 3, 4, of the 4 of these, this one, it has the weakest dispersion forces. These guys, under standard conditions, well, phosphorus is a solid, sulfur is a solid, and iodine are all 3 solids in like your room. Okay? So, anybody know who these solids are, just based on their pictures? This is not red velvet cake, as was guessed in my last class.
Is the top right solid?
The top right, okay, so that's the most common guess, right? But we're doing molecular solids. Molecular solids are not ionic. So who is a very common substance you know in real life on this one that looks like that? Sugar, right? So this is sucrose. It's a molecular solid, C12H22O11. Okay, anybody know who the top left is, the red thing? It's red phosphorus. It's used in, oh my gosh, my brain just, it's used in flares, sorry, okay? Red phosphorus is used in flares. This is solid phosphorus right here, molecular solid, non-metal. Now, this is an allotrope of phosphorus. These two guys are allotropes of one another. What does that mean? That means they're the same exact element, but they have totally different uses and structures. This is white phosphorus, and it has been used in chemical warfare because it really, really burns and stings when it enters any sort of mucous membrane. So like if you inhale it, it burns your throat, your lungs, and they've used it in wars, which is super different than using red phosphorus in a flare, but both solids and both molecular. Anybody know who this is? This yellow crystal looking thing? Solid sulfur. Solid sulfur. Sulfur is not the solid sulfur, but certain compounds that have sulfur in them is what's responsible for like that rotten egg smell you have probably smelled at some point in your life. That's sulfur right here. So again, these are all molecular solids as opposed to ionic solids. Okay, so as of right now, ionic bonds are the strongest we get, and we're about to change that. Covalent network solids are the strongest type of solids that exist. Does anybody know who is the strongest naturally occurring, not man-made, substance on Earth? It is diamond. And does anybody know who makes up diamond? It is carbon, pure carbon, carbon that has been pressurized. So this is, oops, that doesn't show up very well. This is carbon, this is diamond, covalently bonded to itself over and over and over again in tetrahedral fashion. And because of that, it forms this super rigid structure called a covalent network. Covalent because they're bonded covalently, and network because they bond to themselves over and over and over and over and over and over again. And carbon is very versatile in that sense because carbon has 4 valence electrons. So it has the ability to bond 4 times, which is another reason why it can bond to itself over and over and over again in organic molecules, okay? So these covalent network solids are super duper strong. They have the highest melting points, the highest boiling points, and they're definitely stronger than, now you might want to think of them as molecular, right? Because they're non-metals, but they're non-metals specifically right now with carbon that bonds itself over and over again in tetrahedral arrangement. which it forces this network to be very, very rigid and strong. Now, an allotrope, there are allotropes of carbon. One is diamond, the other is graphite. So they're both pure carbon, but they're organized differently. So graphite is an allotrope of diamond, okay? And graphite is like what's used in your pencils, and they bond in a trigonal planar shape. Now, the trigonal planar bonds are really, really strong, but the dispersion forces between the layers is not very strong. So I'll show you what I mean right here. Here you have diamond, right here, where the carbons, carbons are bonded 4 times, over and over and over again, okay, in this very, very rigid structure. Now on here, so like this is a layer right here, and these are still all carbon atoms. Now if you notice, it's kind of hard to show this way, but this is a carbon, 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 bonded in a trigonal planar shape, okay? Trigonal planar, you can see. And now trigonal planar lies flat, so that's what gives graphite the ability to write on a piece of paper, because these layers right here, they'll glide past each other easily, because their only forces that hold it in layers are the dispersion forces. So while the covalent bonds are strong, the dispersion forces allow graphite to slide past itself, which is why it comes off on your paper so easily. It even will come off on your finger if you try to draw on your finger. Again, so because they're structured differently, they behave and act differently. This is a much more rigid structure, whereas this is going to be a softer structure. Okay, now carbon is one element that can form covalent networks. The only other element, or it technically is elements, that can do this is silicone. Why silicone? Well, carbon and silicone are in the same exact family. They both have 4 valence electrons. So silicone also has the ability to do this. So carbon can bond with silicone over and over and over again to form covalent networks, okay? Carbon can bond with itself over and over and over again to form covalent networks. Silicone can bond with itself over and over and over again to form covalent networks, but silicone is more often seen with oxygen. And so silicone, oxygen containing compounds are often referred to as silica. So quartz is an example of a network solid, a covalent network solid containing silicone and oxygen. And again, they kind of form in this tetrahedral arrangement. Now, don't confuse this with glass, which is also silica, silicone, and oxygen. However, glass is made by heating it up, heating the silica up and then cooling it quickly. And because of that, it creates disorder. There isn't this perfect pattern that we see in our normal covalent network solids. There's some disorder. It's kind of distorted when you look at it. Now, boron is actually able to form covalent network bonds as well, but we're not going to focus on that, okay? So glass is an example of what we know as an amorphous solid, meaning it's like morphed into something with disorder. Okay, it's kind of distorted. There's no like set pattern. So maybe this picture will help. So remember, solids with regular patterns are sometimes referred to as crystalline. So like our ionic solids, okay, and now our covalent solids. And then amorphous solids don't have this distinct regular pattern. So look at quartz, which is silicone and 2 oxygens. So the red is the silicone. Let me see this. I'm sorry, the red is not the silicone, my bad. So silicone is in the blue, oxygen, oxygen, but then silicone, it's so hard to write on this. Oxygen, oxygen, and then silicone, 2 oxygens, and then silicone, 2 oxygens. So like each silicone shares an oxygen with its neighboring silicone. But now look at this beautifully repeating pattern, okay? This is a covalent network. Now, even though glass is made of the same elements, do you see that the pattern isn't the same anywhere you look at it? There's lots of disorder. It's not like a perfect pattern consistent throughout the entire thing. So that's what's considered to be an amorphous solid. So this is a covalent network solid, whereas this is an amorphous solid. Does anybody know in nature how glass is sometimes instantaneously formed? Burning sand. That is true. Burning sand, often you can also have like lightning strike the sand, right, which is a bunch of heat and energy. And it can produce glass because the glass is made up of a bunch of silica, okay? So that's a way that glass can sometimes be produced with like lightning hits the sand. If you've ever watched the movie Sweet Home Alabama, which you probably haven't because I'm old and it's like an older movie, her ex-husband has like a glass store, and that's what he does. He puts rods out in the sand and waits for lightning storms to be able to get different like glass structures out of sand. It's pretty cool. Okay, so for solids, we're gonna have two practice problems. What type of solid will each of these following substances form? So let's rehash. We know that there are ionic solids. Those are metals with nonmetals. We know that there's molecular solids. Those are nonmetallic only. We know that there are covalent network. That's the one we just learned, right? Covalent network solids. And the only two things that are capable of covalent networks are carbon and silicone, or silicone with oxygen, okay? And then we also have metallic solids, right, which is just pure metals. So, since these are our types of solids, take a brief moment, please. I'm going to give you about 2 minutes and identify which, based on who the elements are, which types of solids these guys would form if they were able to form a solid. Okay, carbon dioxide. This guy should be molecular. It's nonmetal with nonmetal. Silicone and oxygen, we just learned, are special. They form these covalent networks. Covalent network. Silicone only, also covalent network, but they sometimes are, I'm going to call it like this, they call it atomic network sometimes instead of covalent network because it's just silicone, an atom bonded to itself, okay? Covalent network is fine though, okay? This is methane, non-metal, non-metal. This is molecular. Carbon does not form network solids with hydrogens. Okay. Ru, transition metal. So it's a metal and it's by itself. So this would be just metallic. Iodine is a non-metal with itself. So it's molecular. Potassium bromide, metal, non-metal. This is ionic bonding. Water, molecular, nonmetals with nonmetals, called molecular. Sodium hydroxide, metal polyatomic, ionic bonding. Uranium is a metal, so metallic. Calcium carbonate, metal polyatomic, so ionic. And pH3, nonmetal, nonmetal, so molecular. Any questions on these? All right, one more try for practice. I would like you to identify all forces present in each one of these and then determine which type is the strongest, which intermolecular force is the strongest of these. So I'll give you another minute or so. So here are here are the answers. Does anybody have any questions? The first, if there's more than one type of force that holds the substance together, the first one written is the strongest of the two. So like dipole is a stronger in general interaction than dispersion forces, but it does have both. Are there any questions for this slide? So London dispersion forces are generally short-lived, but if they happen, um, and the more that they happen, the chance of, it's not like something like iodine, for example, only has dispersion forces, but its dispersion forces are so strong that it continues to have them and it will remain as a solid. It won't just like turn into a solid and then like, oh, now they're not dispersed that way anymore and then break back down and like be a gas. Its dispersion forces are so strong that it remains the solid because of that. Okay, so practice FRQ. So it says account for each of the following observations about the pairs of substances, and you want to use principles of chemical bonding or intermolecular forces. And so I'm going to give you a moment and I want you to do your best to thoroughly explain these given what you know now from this chapter. I will go through how to best explain them. I don't need you to write a novel, but you can't just spit out intermolecular forces and be finished. You have to explain that you understand what those types of force mean for whatever physical property that they are discussing, like boiling point or state of matter or melting point, etc. So I'm going to give about, 3 minutes to see if you can get through these, and then we'll get back to it. So the first one says, even though ammonia and methane have similar molecular masses, which means molar mass, okay? Ammonia has a much higher normal boiling point. Remember, the word normal just means at 1 atmosphere, which is normal, like for us at least, normal pressure. So ammonia is harder to boil, is what this is saying. So the question is why? If they have similar molar masses, it means they have similar dispersion forces. So something like this, ammonia is capable of hydrogen bonding, whereas methane, right, because you have to reference both molecules, whereas methane only has dispersion forces, and hydrogen bonding is a stronger type of intermolecular force. So therefore, methane will be harder to boil because it has more attraction to itself. It'd rather stay as a liquid as opposed to be ripped apart and turned into a gas. Something like that. You cannot just say methane has hydrogen bonding and, ammonia has hydrogen bonding and methane has dispersion forces only, and then stop. So what? You have to go on to explain that you understand what that means in terms of boiling point. Okay? So the next one is at standard conditions, ethane is a gas and hexane is a liquid. So we know that hydrocarbons are only nonpolar. They're all nonpolar, which means they only have dispersion forces, but C6H14 is heavier, more electrons, more polarizable. Therefore, it has a stronger attraction to other molecules of hexane. So it will remain as a liquid because it's more attracted to itself, it's more polarizable, whereas ethane is lighter, it's less polarizable, so it doesn't have strong forces of attraction to itself, so it will escape into the gas phase easier. Okay. Silicone melts at a much higher temperature than chlorine gas. Okay, what did we just learn about silicone? Well, silicone can form covalent network solids. They are super duper strong, okay? They form in repeating patterns, and so they are really, really hard to break apart. Whereas chlorine is a diatomic, it's not polar, it only has weak dispersion forces holding the molecule together, so it will melt at it'll melt at a much lower temperature than anything that's a covalent network solid. Okay. Magnesium oxide melts at a much higher temperature than sodium fluoride. So if something melts at a higher temperature, it means it's harder to melt. things that are harder to melt are harder to pull apart. So why? Well, magnesium oxide is +2 -2. Sodium fluoride is +1 -1. So remember that charge trumps size. So the Coulombic force felt in magnesium oxide from the charges, the greater charge, is much greater than that felt in sodium fluoride, because sodium fluoride has less charge with +1 and -1. Questions on this one? Okay. So let's do this one. Explain each of the following in terms of atomic, molecular structures, and or intermolecular forces. Now this one doesn't say you have to mention both molecules, so you just have to justify properly. So I'll give you, actually, I'm going to go through this one with you so we have enough time for corrections. So solid potassium conducts an electrical current, whereas potassium nitrate does not. Solid potassium is a metal. Metallic bonding allows electricity and heat to flow through them. Solid potassium nitrate does not consist of charged particles in the solid state, so electricity can't flow through it. Something like that. Okay, SbCl3 has a measurable dipole moment. That means it's polar. That's what that means. Whereas SbCl5 does not. Well, if you draw these, this is trigonal pyramidal. This is trigonal bipyramidal. Trigonal pyramidal is asymmetrical, okay? Which means asymmetrical shapes, their dipoles don't cancel out through symmetry, making it polar, whereas SbCl5 is trigonal bipyramidal. Its dipoles cancel out through symmetry, making it nonpolar, okay? The normal boiling point of carbon tetrachloride is 77, and carbon tetrabromide is 190. Now, CCl4 or Br4 are both tetrahedral. These would be Cls. I'm not including lone pairs right now for the sake of time. So, tetrahedral shape is generally nonpolar. So these are both nonpolar, which means the only factor that plays a role is they only have dispersion forces. So CBr4 is much heavier, so it has greater dispersion forces. It's more polarizable, so it'll be harder to boil than carbon tetrafluoride, which is lighter and is less polarizable. All right, the last one. NaI is very soluble in water, whereas I2 pretty much doesn't dissolve in water. Well, why is that? Well, sodium iodide is ionic, and ionic compounds have the ability to have ion-dipole interactions with polar solvents like water, whereas I2 is a molecular solid. It's a covalently bound compound, okay? It's non-polar, and water is polar. Things that are non-polar do not want to be dissolved or soluble in things that are polar. Polar goes with polar, non-polar goes with non-polar. And we are going to talk a lot about this in the next topic. Okay, take 1 minute, please, to answer these 4 MCQs. They're pretty short. They're testing on the same exact concept with different types of solids. So these are the answers, and then I just gave examples that would be something like this. Like this would be like sodium, for example. This would be solid sodium chloride. This would be like chlorine. Well, I'll just do Cl2, okay? This would be like HCl. It's polar, so it'll dissolve in the liquid phase. Ugh, I shouldn't have used HCl. That's a horrible example. Ammonia, covalent compound, molecular, does not break apart into charged particles, but it's polar. In fact, it's capable of hydrogen bonding, so dipole-dipole forces will let it be soluble in water. Okay, last thing before we move on to our test. So a lot of these intermolecular forces directly relate to a lot of substances in biochemistry, right? The chemical interactions that happen in living things. So remember that proteins, if you don't remember, are these really, really big, long macromolecules, that means big molecules, that are formed from a bunch of amino acids just linking up together. They form these, these peptide bonds. That is the process of in chemistry, a dehydration reaction where the water is removed and the peptide bond is formed over and over and over again. Now, some of these molecules have hydrogen bonding, some have dispersion forces. It depends which atoms are where. But again, these forces we talk about in this chemistry class also can be seen present in biological processes. So look at, this is water, so the OH group and the H group. So this is an amine. This is called a carboxy acid. Well, amino acid, but it's okay. You don't have to know that. These two guys come off. Water comes out, dehydration, and then they link up, and this is called a peptide bond. And then this happens again and again and again, over and over and over, until you just create all of these different peptide bonds, and these links of amino acids make up proteins. So again, that's all chemistry involved right there. Your DNA forms an alpha helix and your beta pleated sheets because of hydrogen bonding. So the oxygen of that's attached to the carbon is attracted to this hydrogen that's attached to a nitrogen. So this hydrogen will hydrogen bond with this oxygen, which is what causes the helix to form and make that shape, is all because of the intermolecular force of hydrogen bonding. And then the same with the beta pleated sheets. They're also held together by hydrogen bonding. That's an intermolecular force. Enzymes. So we're going to do a pretend. We're going to say this is lactase. That's an enzyme. Okay. And this is lactose, right? The sugar found in milk. Lactase helps break down lactose, right? People who are lactose intolerant don't do this, or don't do this very well, and that's why any dairy products can be hard for them, because lactose is found in many dairy products. But again, the reason that the lactose, for example, is attracted to this active site of the enzyme is because of intermolecular forces, depending on what they are, right? And so the lactose is attracted, for whatever reason, to this active site of this enzyme, and that allows the enzyme to attract it, bind it, and then break it apart into simpler parts that make sure, body tolerate the sugar coming from those types of products. Again, look at, you've got this sort of organic molecule, a bunch of carbons and hydrogens. This is super all carbons and hydrogens, so dispersion forces inside. However, look at all of these guys that are able to hydrogen bond on the outside. Okay, so this substance would be able to form hydrogen bonds with water because of whoever's sitting on the surface. Okay. All right, that's it for liquids, solids, and intermolecular forces.